In a laboratory at the University of Warsaw, a team of physicists decided to incorporate a detail that many studies often overlook: what happens when atoms interact not only with light, but also with each other. This small methodological change led to an unexpected observation. Under certain conditions, atoms can be organized collectively to emit light in a synchronized and more intense way than usual. If you like science and innovative discoveries, don't forget to subscribe and like this video, so you can keep up with the latest advances in quantum physics and other fascinating topics. Your support is very important to us. This emission, known as superradiance, was already a phenomenon described for decades. However, the new study reveals that there is a completely different phase of the system, which only appears when the quantum intertwining between light and matter is incorporated. This opens new doors in the understanding of quantum physics. The work, published in Physical Review Letters and directed by João Pedro Mendonça, along with Krzysztof Jachimski and Yao Wang, deepens the mechanisms of superradiance. It shows that this phenomenon can be altered by the local interaction between the atoms themselves, challenging earlier models that simplified quantum physics. In quantum physics, light and matter systems are often studied in optical cavities. These microscopic spaces allow light to bounce between very close mirrors, creating a stable environment to study their behavior. Here, atoms interact with trapped photons, acting as part of a coordinated set. One of the most striking examples of this collective behavior is superradiance. Instead of emitting light in a disorderly way, atoms synchronize their emissions, generating a much more intense pulse. However, many theoretical models simplify this phenomenon by ignoring direct interactions between atoms. The new study breaks with that assumption. By introducing short-range dipole-dipole interactions, researchers observed that they can amplify or weaken superradiance. This allows us to foresee situations in which this phenomenon should not occur, and yet it appears. One of the key concepts in this research is quantum entanglement. This property connects particles so that their states are correlated, even at a distance. In this study, intertwining includes both atoms and photons, allowing the system to act as a whole. Light-matter systems confined to optical cavities are a key platform for emerging quantum technologies, including quantum batteries, which promise to charge faster and more efficiently. Research shows that local atomic interactions act as adjustable parameters to modulate this behavior. The new approach developed by the team explicitly includes entwining. This method reveals how atoms correlate and how these correlations affect interaction with light. This allows to detect an ordered new quantum phase that shows superradiant properties without the usual parameters. The deeper value of the study lies in the proposed approach to studying complex quantum systems. By incorporating the entanglement from the beginning, researchers suggest that many previous approaches might have left out important behaviors. This can make the difference between a functional design and an unstable one.